Hello, my name is Robert Hassanov. I'm a PhD student at TU Dresden, Germany. I want to present our work on domain-specific hybrid mapping for energy-efficient baseband processing in wireless networks. Welcome to my talk. Today, 5G networks are expanding in many countries. Compared to its predecessor 4G, 5G has to fulfill high requirements. It needs to process thousands times higher data traffic, connecting 10 to 100 times more devices. All requests must be processed 10 times faster, within 1 millisecond. In addition to traditional mobile broadband, 5G will connect billions of IoT devices, as well as it will be used for mission-critical applications that require uninterrupted and robust data exchange. To deal with these high requirements, baseband processing has seen a trend towards software implementations. In traditional radio access network, remote radio units were connected to individual baseband units. Then this was moved to Cloud Run, where baseband units formed a pool. And currently, these pools employ virtualization techniques, for example, network functions virtualization. To support virtualization, more general-purpose hardware is used instead of COTS-based devices. However, this solution leads to worse energy efficiency, which is actually critical. According to the studies, the energy demand of wireless networks will rise dramatically in the next 5–10 years. By 2030, it could even reach 1,600 terawatt-hours per year. This is half of energy consumption of all European countries in 2020. To address energy efficiency, we propose adopting the method of model-based hardware-software co-design, or more specifically, a hybrid mapping approach. This method works well with the dynamic workload, which is the case of baseband processing. Here we see the typical hybrid mapping flow. The generation of mapping is split in two parts, the design time part and runtime part. At design time, each application is analyzed individually, virtually in isolation. Given the model of the application and the architecture in the input, we may generate a set of partial solutions, which we call operating point. Each operating point is characterized by its mapping and energy and performance values. The Pareto filter set of operating points are supplied to the runtime resource manager. The resource manager, in turn, analyzes the current workload, its requirements, and the system state for each application. It selects the proper operating point, performs necessary transformations, and generates a special temporal schedule in which the multi-application mapping is defined on subsequent segments. Hybrid mapping approaches are quite used in the literature. These methods prove to improve the quality of the found mappings in terms of energy efficiency and performance. At the same time, the execution is held in a predictable manner. In the following slides, I will describe the baseband processing flow, and then I will talk about how we can use the hybrid mapping approach in baseband processing. This slide describes the frequency allocation in wireless networks. In each base station is allocated a frequency band split into subcarriers. The time domain is split into subframes, 1 millisecond each. Each subframe contains 2 slots, and each slot contains 7 symbols, 6 data symbols and 1 reference symbol. The minimum allocated frequency for one user equipment is called physical resource block, or ERB. By user equipment, we mean a phone or other device which is connected to wireless network. The parameters of user equipment vary within a number of ERBs, number of antennas, layers, and demodulation scheme. Additionally, user equipment could vary with type of communication. Along with enhanced mobile broadband communication, 5G networks supports massive machine time communication and ultra-reliable low-latency communication. According to the standard, in the first two cases, the request must be processed within 2.5 milliseconds. while for ultra-reliable, low-latency communication, the deadline is half the millisecond. To meet these deadlines, we must use very fast algorithms for runtime scheduling, which work within 100 microseconds or even faster. This slide shows the baseband processing flow per user equipment. The top row of the task is used for evaluating the distortion of losses of the user signals. Then, in the bottom row, the signals from different antennas are merged, and the original bits are recovered. Many tasks in this flow could be parallelized, and the parallelization factor varies from phase to phase. So, the application graphs and timings of baseband processing flow depend on the parameters of user equipment. Due to that, we have to generate partial solutions for each set of parameters at the design time of the hybrid approach. On the right side, you see a more general representation of the application model. Assuming the parallelization factor, this graph consists of more than 100 tasks. Existing methods of design space expression, for example, genetic algorithms, do not work fast with such a large number of nodes. However, this application has a so-called phase sequential structure, in which the execution of the application is split into phases. Using this knowledge, we propose a fast mapping heuristic called phase@fast, which performs a mapping of the application phase by phase, and within phase we make sure that the hardware resources are loaded near evenly. The heuristic also evaluates the execution time and energy consumption of those generated mappings. We vary the set of available resources, thereby generating a parity set of operating points. As we mentioned earlier, our runtime heuristic must be ultra-fast to meet application deadlines. To our best knowledge, the fastest and efficient runtime algorithms are based on multiple-choice, multidimensional knapsack formulation. In this formulation, we express the capacity of the knapsack as multidimensional values, in which each dimension refers to a specific processor type, and the values represent the sum of execution times on all cores of this type. The operating points of each application form a group of items, and exactly one item must be chosen in each group. The goal of the knapsack problem is to maximize overall value, which means in our case to minimize the overall energy consumption, since we use negative energy values, energy consumption as a value of each item. To deal with the task, we used our heuristics, which prioritize user equipment, which has the most energy saving potential. It schedules all applications in a joint manner, unlike an approach with iterative scheduling. And in order to further reduce the runtime overhead, it reuses the pairs that generate schedules. Due to the time limitations, I don't provide the specifics of the algorithm, but I will be glad to explain it in a Q&A session. Let's move to the evaluation. In our experiment, we took the open source implementation of the LTE5 benchmark. We extracted the execution time of its kernels by running on Odroid XU4. The extracted execution times we used to model the application behavior in Moccasin. Moccasin is a simulation framework for rapid prototyping written in Python. In this framework, we used the model of Odroid XU4 and the virtual platforms. We developed different runtime strategies for comparison and evaluated using 5 different traces. 4 of them are real LTE traffic traces. All these models and algorithms are available in the open source plugin of Moccasin. First, we evaluate our design time heuristic against other existing algorithms. The evaluation is done in terms of exploration time, the left plot, and the quality of generated mappings in terms of execution time and the energy consumption. In these plots, our phase-fast algorithm is used as a baseline and marked with dotted lines. As I said before, the existing mapping techniques do not work well with such kind of graphs. Only simulated annealing could generate the mappings of similar quality as ours. However, it requires 4 orders of magnitude more time for exploration. Next, we evaluate the runtime part of the algorithm. Here we see the overview of the evaluated approaches. As a baseline, we use a dynamic scheduler, which we assert is the open source implementation of the Phi benchmark. For hybrid approaches, we compared 3 different time-based algorithms. Along with our algorithm, we evaluated the version with iterative scheduling of user equipments and without using the previously schedules. As the last algorithm uses the Lagrangian relaxation technique. This slide shows the ratio of the successfully executed user equipments requests and the overall energy efficiency. The hybrid approaches outperform the baseline up to 30% in terms of success rate, while the dynamic energy consumption is dramatically reduced up to 80%. Note that in gross terms, all hybrid approaches are on par. However, they require different times to generate the schedule. And we may see it in this plot. The algorithm with Lagrangian relaxation is very slow, taking almost a second to schedule the task. Among MDF-based algorithms, our proposed algorithm outperforms the iterative version by nearly 40% on the phase 4, the heaviest trace now. Workload. The absolute values of our algorithms are still too high to be used in baseband processing. As already mentioned, the prototype is implemented in a framework written in Python. We expect significantly lower runtime overhead in the implementation written in low-level programming languages like C or C++. To conclude the talk, let me summarize the main points. In this work, we have investigated the hybrid mapping approach and its applicability for baseband processing. In this approach, we leverage the particular computational structure of the task graphs to improve the design part of the algorithm, as well as at runtime we refine the runtime mapping algorithm. Both these lead to a better success rate and energy efficiency. In future work, we plan to apply our methodology on the benchmark based on the 5G standard, as well as we want to address more performant hardware platforms. In addition, we also plan to address the interplay with voltage frequency scaling, which may save more energy. With this, I would like to finish my talk. Thank you very much for your attention, and please come for Q&A after the session.